I'll talk in the next 25 minutes about the work we did with optimizing our nuclear physics code for KNL. I'll start with a brief summary of the kind of work, physics that we're doing, optimization target, and then the result. What we're doing is nuclear physics. The degrees of freedom that we have are protons and neutrons. And what we're trying to do is, given a Hamiltonian consisting of the kinetic energy plus two-body forces and quite often also three-body forces, solve the quantum many-body bound state problem for typically of the order of 10 particles. We do that by expanding the wave function in anti-symmetrized products of single particle states. That's often referred to as a CI, configuration interaction calculation. It's similar to methods are used in quantum chemistry and electronic structure calculations, but the kind of truncation of the basis is often different in the different subfields. Computationally, what it translates into is that we're constructing a very large matrix, the order of 10 billion by 10 billion, but it's very sparse and symmetric. And then we want to obtain the lowest eigenvalues and eigenvectors. We have a code that does that. It's been in the development for about 25 years now. I've been involved in it for 9 years. Right now, it's more or less platform independent as long as you have OpenMP and MPI. It's mostly Fortran 90. And it's essentially two phases. One where you construct a matrix, and the second phase where you obtain the eigenvalues. Until now, roughly, we used Lanczos algorithm, iterative sparse matrix vector multiply is the most compute-intensive kernel there. Right now, we're switching over to LAPCG, and I will come to some of the details there in a few minutes. The biggest calculations are actually limited by the aggregate memory of the system. We want to get to larger nuclei and larger model spaces in order to get a more accurate result. But it's limited on current machines to about 10 to the 14th non-zero matrix elements, and that would need about a petabyte of storage. In order to store it, since it's a symmetric matrix, we only store half of the non-zero matrix elements. But the price we pay for that is that we have to do a sparse matrix vector multiply as well as a transpose sparse matrix vector multiply with the same data structure. And that will have consequences for cache use and also possible race conditions depending on how you store it. The sparsity structure that you would naively get is something like this. Black means a non-zero matrix element, and this is actually a pretty, I don't know, this is probably about a 10,000 by 10,000 matrix, so it's all the dots are in fact dense regions. In order to get load balancing, we distribute the basis that we generate in a round-robin fashion over the MPI ranks that we have. So in red, I've overlaid the actual MPI processor. So each of these squares is assigned to an MPI processor, and even though these looks like identical squares, they are actually all different. That way we get almost perfectly load balanced in terms of number of non-zero matrix elements, the local dimension on each matrix, etc. The price we pay is that it's rather difficult to find the non-zeros here compared to here. So there is a price we pay. We do have a reasonable, efficient method to deal with that. A little more closer into the sparsity structure that we get. If we have an A-body bound state problem with a many-body problem with a few-body interaction, then we only get non-zero matrix elements if most of the particles, the many minus the few particles, are in identical single particle states between the row and the column. So this, looking at the quantum numbers, or rather the labels for the single particle states, is what tells us the sparsity. We deal with this by tiling based on the quantum numbers. That leads to these dashed red lines here. and you can see that quite a number of these tiles are 0. They're completely empty, so we don't have to go through that. And then in the ones that are non-zero, they're still kind of sparse, but have a quite regular structure. This is a blow up, I think, of that square there. Yeah. And then we combine these into approximately square blocks for the actual SPMV and SPMM. The reason for using blocks there, until about 2 years ago, we used compressed sparse row format for storing the matrix. That works fine for the SPMV, but there is an issue with the transposed SPMV. There's a race condition if you're not careful, if you do it on multi-threaded. The way we deal with that until about a year or two ago is having private output copies for the transposed SPMV. It's clear that on KNL, if I want to have 256 threads, I should not have 256 private output copies, both for time and for memory. So that was one of the motivations to look at alternative formats, and we are now using compressed sparse block format, which also has a couple of other side benefits. It improves, in general, the data locality and cache performance. We don't have this issue with OpenMP race conditions. And the other advantage is that we're moving from a Lanczos algorithm where we have only one vector on the right-hand side to a block algorithm, LAPCG, locally optimized block preconditioned conjugate gradient. And there we have 8 or 16 vectors on the right-hand side. Again, if we would do that with private output copies, things would explode rather quickly. A few words about that LAPCG algorithm. Here I compare the Lanczos algorithm for the first 5 states of a particular nucleus, and we need about 250, 260 iterations to get these all converged. With the LAPCG algorithm, if we start with an initial guess coming from a smaller model space and use a suitable preconditioner based on the diagonal matrix tiles, then we can get the same number of states converged in about 50 iterations. Of course, per iteration, in this case, we would do 8, the equivalent of 8 SPMV. So in terms of number of sparse matrix vector multiplications, we did almost about 1.6 times more work, but the total result is actually a factor of 2 faster, and this was on Edison, I believe. Of course, how much it is faster depends on the implementation and the platform. So now second half is the actual optimization that we did for the KNL. The results I show are all on the KNL white boxes at NERSC using 64 cores, 16 gigabyte of MCD RAM, 96 DDR. The production target system would be Cori Phase 2, and in the long run, we also hope to port this to Aurora in a few years. The comparison with Haswell Cori Phase 1 at NERSC, and since I don't have access yet to more than a single node there, I only look at the single node performance. However, I don't want to look at a small problem because small problems have a very different characteristic than the actual problem I want to look at. So what I did was I create a workload for one particular MPI rank or one particular block of my matrix that would run on 5,000 nodes. So I simulate one node out of those 5,000, which leads to, if I have one MPI rank on that one node, a local matrix of about 100 million by 100 million with about 8 billion non-zero matrix elements. And so this is all of the results that I show are based on this proxy for the actual calculation. And what I do is construct a matrix and then do a number of SPMVs or SPMMs on that matrix. It does not have the additional steps in a diagonalization program like orthonormalization, communication to synchronize, etc. I'm using the Intel 16 compiler, I think. Most of the results are 1 MPI rank per node because that seems to be most efficient for us. I will come to that in a minute. We do explicit memory placement with memkind library and fastmem directives. And most of the results, I think actually all of the results that I show, except for one slide, are in quad flat mode. As far as deciding on what is good, what is bad, especially in the initial phase, I don't have any flops in my code. It's all quantum number comparisons, integer comparisons, bit representations. So what I have is several timers built in the code, and I'm looking at those timers. And so what I want to do is reduce the time to completion for a specific task. First, why do I decide on 1 MPI rank per node? Well, there's two reasons. One is one of them is here. The construction phase, it doesn't actually matter whether you have 1 MPI rank per node and all OpenMP, or several MPI ranks and a reduced number of OpenMP threads. It's completely independent, these first three timers, which is the counting of the non-zero tiles, the counting of the non-zero matrix elements. Then you can allocate the memory for the actual matrix, and you construct the matrix. The actual SPMV or SPMM, you do see a difference. And what we actually want to do in practice is an SPMM on 8 vectors typically, or maybe more. And for that, the 1 MPI rank per node is most efficient. Why this is so much more efficient than the others, I will get to it towards the end of the talk. The other reason for having 1 MPI rank per node is that for some of the applications, we have an actual rather large input file. Currently, the largest input files that we deal with are about 6 GB, and every thread has more or less irregular access to that 6 GB file. So if we have 4 or 8 MPI ranks on a node, and I would have 6 GB on each of those MPI ranks for that array, I will run out of memory a lot quicker than if I can get away with only 1 MPI rank. Scaling with the OpenMP threads for this particular problem is essentially perfect up to 64 threads. Hyperthreading helps a little bit, but not much. This is actually true not only on KNL, but also on Haswell. These fainter lines here are an illustration that it's really the hyperthreading that's failing here, not the lack of parallelism. If I have these 8 OpenMP threads, if I have those all on 2 cores and only use hyperthreading, I get rather poor performance already at 8 threads. So it scales perfectly with the number of cores, and then the hyperthreading helps a little bit. The reason for this deviation in the SPMM on Haswell is that these were generated with 1 MPI rank on 2 sockets, so there is a NUMA issue there, and I believe that's what causes this kink. Hyperthreading does not actually help in the SPMV or SPMM on Haswell, so the comparison with Haswell is done without a single thread without hyperthreading, so that's up to 32 cores on Haswell compared to most of the time 256 threads on KNL. This is a summary of the performance compared to Haswell based on the various improvements we made in the last half year roughly. We started with the pre-KNL version from April of this year. In April, I went to a dungeon session in Portland, and that's when I started to get real serious about specific details for KNL. In red, on the dashed bars are all on Cori, the solid one on KNL. Right out of the box, KNL does worse than Cori Haswell for essentially all phases except for the SPMM. Improvements made in the first couple of months of this between April and June. show an improvement both on Cori and on KNL, but still KNL is worse than Haswell for the setup phase. The matrix multiply actually reduced significantly if you use both DDR4 and MCD RAM, and I will get to details of this towards the end if I can pace myself. I should be able to get there in detail. Over the summer, I did further improvements, and I get now results on KNL that are slightly better than the original Haswell timing, but it's still a little bit worse than the optimized Haswell timing. I spent most of my time over the last couple of months on this phase. Some of the improvements that I made here, I've started to try to carry over to these two phases, but clearly there's more work to be done here. So the rest of the talk I will focus on what I did to get these bars down, first to this level, then to that level, and also how I go from here to here. The other thing is this is for one particular problem size, and of course I'm interested in more than one problem, and every problem has its own characteristic, and whether I was lucky or unlucky in picking this. In hindsight, I was actually pretty damn lucky exactly how I picked it, but I did not do it on purpose. Okay, before going into detail of how we got improvement, a little bit more on what we actually do in that counting phase. We have an A-body problem, or, well, both are A's. A many-body problem with a few-body interaction. So what I need to do is comparing the quantum numbers or the state labels between my row and my column states, or in physics language, between a bra and a cat. There's essentially two different ways how I can represent my many-body states. I can either represent them as a list, an array of single particle indices. So if I have an A-body system, I get A integers here. And because these are antisymmetric products of single particle states, because fermions are antisymmetric statistics, this list, you can get set this up so that the list is an ordered array where the next integer is always larger than the previous one. You never have repeated labels, and it's always bigger than 0. The size of the problem that we look at is typically a few hundred to a few thousand single particle states, so we use 16-bit integers to represent this. The other way of representing this is a bit representation, which is essentially a 0 or a 1, depending on whether a state is occupied or not, which is very efficient if you have a lot of particles and not that many single particle states. However, we have of the order of 10 particles and maybe a few thousand single particle states, so we would have really a very long array of zeros with only very few ones. Now, the type of truncation, however, that we use has most of the time the lower states are more likely to be occupied than the higher states in this bit representation. So we actually also have what I call a truncated bit representation, where I take the first 8 or the first 16, or actually in practice the first 64 bits here that carries most but not in all of the information. So that's how we start, and this is schematics. I first do a column bit representation. I should get this cursor away there. This is a schematic of the code that we have. We first count the non-zeros, and then non-zero tiles, and then we do the further counting. This is the loop that I go through. This bit rep is the truncated bit representation. I do an exclusive OR between the column and the row, and then I count the number of ones in that exclusive OR. If that's larger than twice the rank of the Hamiltonian, it's potentially non-zero. And then I have to do a more detailed calculation, comparison of the states in detail to see whether it really is non-zero or not. And then I can actually get the actual matrix element. So both for the counting of the tiles and the counting of the non-zeros, I go through loops like this. And then when I store them in compressed sparse block format. The first improvement that we did was going from a 32-bit representation to a 64-bit representation, because that simply filters out more of my zero matrix elements, and it essentially is the same time to do a 32 or a 64-bit comparison. The next step was, can we vectorize that? The problem then was that there is no vector instruction for the Fortran pop count function. Well, not I, but some of my collaborators did actually manage to get a manual pop count and vectorize that, and they could get performance that was on, oops, I didn't mean to do that. They could get performance that was on par with the Fortran pop count, intrinsic pop count function. So yes, it can in principle be vectorized and give improvement, but not an improvement over the just compiler standard pop count. The other thing is that the detailed comparison has a lot of branching, has cycle and early exits, etc. So what I did over the summer was get rid of all these early exits, get rid of a lot of the branching. It means not dealing with some of the exceptions that I have there. It also means that we do a little bit more work. I also padded the arrays to prevent any out-of-bound problems, so I didn't have to check, am I at the end of my list or not. Naively, these changes would lead to a slightly larger workload, and that's indeed what you'll see in the next slide. It also means reducing 120 lines of code to about 20 lines of code, which is a lot easier once I want to vectorize it, because that's the next step that I wanted to do. So this first step leads to a code structure like that. I have split up my inner loop, the loop over the rows, into first do all of the pop counts, get a list of the states that pass this test, and then just with that list, I do the second test rather than have this all in one loop. If I do that, I go from the original 64-bit representation was this. If I simplify it and do a little bit more work, it does get a little bit slower. But then if I split this up into 3 separate loops, I get quite a significant improvement, and that's most likely due to an improved cache performance, though I have not actually checked that with performance tools to see whether that was the cause. The next step that I did is, can I take these loops and vectorize them? Well, we know already there's a problem with the vectorization of the pop count, but apart from this pop count, everything else could be vectorized, and by splitting it up in even smaller parts, and I split it up in parts of length vector vector lengths that I can vary through a preprocessor. These are defined at compile time. The bit representation exclusive OR could be vectorized. The pop count cannot. Then the detailed comparison could be vectorized, or rather it's inlined and then vectorized. And there's some unrolling of a loop that's inside here. And then this is also vectorized. So we did manage to vectorize essentially everything except for the pop count. And if we do that, we get at all these results. Now, this is a lot of data. This is the vector length that I used to split up that loop. If I set that to 1, I kill all the vectorization right there. So this is essentially the same as that. So that's a sanity check. Do I have the same? Yep, I have the same. I should also mention blue is without hyperthreading. 2 hyperthreads helps a little bit. 4 hyperthreads helps a little bit more, but not that much. If I go to a vector length of 8 or 16, I see a significant improvement. Beyond 16, it deteriorates a little bit. I don't understand quite why. 16 is also the natural choice for the AVX 512 vector width, so this is what we stick with. That's the status of that part of the code. In the last 5 minutes, I will talk about the SPLM. We use, as I said already, compressed sparse block format. I have to define what the block size is. Of course, the ideal block size depends on the sparsity of your matrix, but the ideal block size is also dependent on the sparsity structure, because I don't want to divide up the tiles that I have. The other consideration is that in order to not exceed the memory that we had from the contrast sparse row format, I use 16-bit integers for the addressing within the blocks, which means the block size has to stay under 32,000. The problem that I study right now, and I summarize the result, the characteristics here, the best value of this block size is somewhere between 8,000 and 32,000. The results I presented are mostly with 16,000. If I make the blocks too small, then I have to make my tiles smaller, and then counting and constructing the tiles will be a disaster. If I make my blocks too large, then counting and constructing the matrix elements within a tile gets too large. So there's kind of a sweet spot for this particular case that's around 16,000. The other thing that we played with, was this indeed the next one? Yeah. Is the memory placement. This is a comparison in red between Haswell, green running completely out of DDR, blue KNL and cache mode, and yellow with placing the matrix in DDR and the vectors in MCD RAM. And for this problem, the set of 8 vectors is 15 gigabytes, so that's a perfect fit. Accidental, honestly. The matrix itself is 60 gigabytes. So we use clearly both quite intensively. And with 8 vectors and this memory placement, we get a significant improvement over Haswell and also, of course, over the other KNL options. The actual memory bandwidth measured here, I think, was 71 gigabyte per second out of DDR and 300 out of MCD RAM. How does it compare if I look at different number of vectors? I showed already for 1, 4, and 8. If I increase it further, my performance goes downhill again. This is all time all what I show. And that's because my vectors get too large. If I go from 8 to 12 or 16 vectors would be 30 gigabytes. So half of this is coming out of DDR again. So that's why this goes bad. If I do a different problem, and this is a problem where I have not only 2-body force, but also 3-body forces, then the matrix is denser. Well, it's still pretty sparse. It's like 1 in 100,000 instead of 1 in a million. It does mean that the SPLM efficiency improves, and we can go up to 32 or 64. Even with 64 vectors, we use 8 gigabyte 40 vectors, so that easily fits in MCD RAM. And if you look at the difference from here to the best performance here at 32, that's a factor of actually, I think it's 16.9. So that's really the vectorization. Of course, there's also an improvement in cache performance, and I have not actually looked with performance tools what is the main source of the improvement. Okay, that's about all that I have, and I still have a minute on the clock. So the performance summary: original code on Haswell versus optimized KNL on a single MPI rank. We get a factor of 1.2 improvement in the initial counting phase. It's a little bit worse on KNL than Haswell, a little bit slower on KNL for the constructing of the matrix, but there's still work to be done, and especially in the last couple of days I have some new ideas of what I should try and how I should look at where I can get some improvement. We get roughly a factor of 2 improvement in the SPLM. Vectorization, as I said, remains a challenge for the matrix construction. But with this block algorithm, it does work for the diagonalization phase. Okay, that's about it.
I think we have time for one question, if there are any. Okay, so a question from me. So there was one of your bar charts, it looked like between June and August, your KNL performance got better, but your Haswell performance got worse. and I'm just wondering if you could elaborate on what happened there.
That was when I broke up that loop over the row states into these a double loop with a vector length of 8 or 16 there, and I simply ran it on Haswell with the same 16 as that I was using on KNL. And I don't think that's the optimal setting there, but...
Okay, let's thank our speaker.